knowledge and no knowledge at the same time. I'm going to just start off with a slide about what rammed earth is not. We just started with a little film from, I think, America, and they're adding cement to their mix. And adding cement to the mix is something that we just don't do. If you need cement as a binder, then really you should be making concrete and not calling it earth, because it's just a confusion. I'm just showing this slide because it shows the figures from the UN, which says that every ton of cement which is produced produces 1.25 tons of carbon dioxide. And there's an issue there because, well, these little shells are about the size of your red blood corpuscle. Inside that ring of calcium, which is the shell, there was a little piece of carbon, and that piece of carbon was taken out of the atmosphere up to, 4, 6, 800 million years ago, and deposited at the bottom of the sea in a very stable form. And the way that we make cement is to burn that piece of carbon out of the shell and put it back into the atmosphere in the form of carbon dioxide. When that shell was forming, it was taking carbon out of the atmosphere, which allowed us to exist as a species, breathing oxygen. And now what we're doing is trying to revert ourselves back to that earlier period where the atmosphere was not breathable to us as humans. And we just prepared a little graph about this, which compares the carbon dioxide which is being emitted from aeroplanes with the carbon dioxide which is being emitted from cement over the Kyoto period. So from 1990 up to the latest figures we have is 2014. So you've got these three lines at the bottom, which is CO2 emissions from aviation, from aeroplanes over that period, and the grey line above is the CO2 emissions that we have from cement over the same period. And you can see that the emissions from cement are rising very, very fast, and much faster than they are from aviation. So this is one of the reasons that we don't use cement in our mixes, and one of the messages that I'm most keen to promote about this material is that although in America and Australia a lot of people use cement, we do not. The next slide just kind of emphasizes this point a little bit more, talking about monopolies and why it's not so easy to build with earth in a modern context, and this will be as true in Poland as it is in the UK. Legislative monopolies, building regulations, standards tend to focus on materials like cement and steel, and they in turn lead to financial monopolies. Will lend you money, will insure your building as long as you follow the building regulations, which is about cement and steel. And then professional monopolies will train you to be an architect or an engineer, but obviously we're going to train you to follow the building regulations, and therefore not earth, but more cement and steel. And at the bottom you've got research monopolies, where again funding from government and industry tends to be funded in such a way that it supports industries like cement and steel. So you have this situation, and our job is to try and work out how to get around some of these things and move earth to being a more normal type of material. Okay, so that's the heavy stuff. And then the next question that quite often comes is why earth? What is apart from these emission issues, what else can earth offer? And so this is an image of a termite mound in West Africa, and it's in an area where the temperature can go from 40 degrees Celsius in the day to 0 degrees at night. And it's sheltering organisms which are very sensitive to temperature, and they're using only the materials around them which they have to make a stable environment, and the material that they're using is earth. And with the earth and the way that they're designing, they're able to stabilize their environment to such an extent that they have a very low temperature range inside, which I can illustrate to you a little bit more what the inside of this structure is like. The white areas have been filled with plaster of Paris, so they are air, and they're surrounded by this clay structure. And within that structure, the termites farm a kind of fungus, and the fungus is extremely sensitive to both temperature and also humidity. And if the fungus dies, then the termites die, because this is their food source. And so they found that using earth is a very effective way of being able to control both temperature and humidity in an area where the temperature diverges by 40 degrees in a 24-hour cycle. So earth has got a lot going for it in terms of how you use it and the kinds of environments that you can build with it. Termites have been doing this for 400 million years, and they're extremely advanced. And we've been doing it for, a few thousand years, and we have a lot to learn. And for me, that's kind of a part of the excitement of using the material. Rammed earth is just one of a family of earthen materials. It's one of the denser earth materials. And it's been used around the world. It's been used on every continent except Antarctica. And there are a whole set of common features to do with the use of the material. Things like not moving material very far. So in this case, this is a building in Bhutan where the building is on the side of a mountain, and the material has been dug from where the building stands. Oh, let's move for me. So now we're in China. The same thing is true. The material is being dug from where the building stands. It's then processed, in this case by a group of women who are taking the material up to the ramming team, who in this case are largely men. And all of the material is being processed by hand and moved by hand and compacted by hand. We've been in a situation, West Africa, where the opposite is true, and women do all the ramming and the men do all of the material preparation and placing. And it doesn't really matter as long as the correct conditions for the material. Oh, it's moved again. I don't know why the slides keep moving, but anyway. So this is Morocco, and Morocco has an enormous quantity of rammed earth structures. We're looking in this image to a new town from the site of an old town, and the old town has 3 or 4 story buildings. The new town has 1 or 2 story buildings, respecting the newer building codes. And again, this form of formwork, this is in Morocco, but it looks very similar to the kind of formwork in Bhutan and Peru and many other places. This is the kind of formwork that I started with when I began practice in the mid-80s. 2 wooden sides, 3 sets of ribs, and some very basic rope ties that holds the work in place. Historically, there are a lot of amazing examples. This is in Spain. This is Granada in Spain, the Alhambra. But of course, the Great Wall of China was very largely rammed earth. So some parts of it have got brick or stone facings, which it's an aspect of building with rammed earth which has been used many times across the centuries and in different places, that it can be plastered or finished in lots of different ways. So, for instance, this is an example from Portugal. This is somewhere in the 19th century. It's a plastered example. But at the same time, in the 20th century, in Portugal, Rammed Earth has been used in a more modern context where some finishing has been done, some plastering has been done, and some of the work is left expressed and visible. And this is an aspect of the work which is interesting. It goes through different fashions. People want to see the Earth and they think it's modern and interesting, or they don't want to see the Earth because it's old-fashioned and poor. And really, the Earth throughout all of these things, whether it's rammed by men or women, or in China or Peru, or whether it's covered or it's not covered, the same aspects of the Earth are remain, which is that if you do it correctly, then you can do all of these things by men or women, or covered or not covered. There's a big history of earth building, obviously, wherever humans have been. Typically, humans live where there is soil, and soil can be used in lots of different ways. This is central France. I don't have images from Poland, but I do know that there's some quite interesting work was done by a woman called Marta Zurakowska, who was at that point studying in Scotland, and she gave a paper presentation where she talked about earth building after the Second World War, which was at that point supported by the Polish government and by universities and other institutions, and which then fell out of favor in the 1960s. But she says that Polish building standards prepared during the 1960s contain all the essential information about earth walls, plasters, and mortars, but they're now forgotten. So I guess if you dig a little bit in Poland, you'll find more of this kind of information. This is also France. When you get into earth building areas, you find that everything is built with earth: commercial buildings, housing, the fire station, the church. Everything is made from earth. One of the questions that we're very often asked: how high can you go? This is a German example from the former East Germany, which was built in 1820. It's 7 stories, and it's built from the material that was dug out of the basement to form a cellar. It's not very attractive. It's not very beautiful. One feels that architects today could make something a little bit more interesting to look at, but nevertheless, it's been there for coming up for 200 years, and it answers this question about how high can you go. This is the closest equivalent we have in the UK. This is from the 1840s in the South End in Winchester. And this is built with a material called chalk, which is not to be confused with calc. It's a lime-based material, but it's very soft. And they dug a lot of it up when they were building railways, and they thought, what shall we do with it? And they decided they would build some houses. So there's quite a lot of buildings like this in the southeast of England where we have big chalk deposits. So, Rammed Earth. I'm going to move around in different projects and talk about different aspects, but just quickly to say there is no one answer to what formwork and what material you can use. It's quite widely applicable. So this particular project is a workshop, and we're using formwork made from old scaffold planks, and they're fixed together and bolted through quite simply using a mix of material. Sorry, the sound interference sounds like a rammer, which I don't know what to do about that. Sorry, I don't know what quite happened there. So yeah, this is very basic formwork using scaffold planks to make a structure which is about 5 meters long and 2.5 meters high, and we rammed this all by hand in about a day and a half with a group of architects. Rammed earth is a cast material. It's the form that you make, the formwork that you make, is the negative shape of the wall that you finally build. So in this case, you've got a wall with a piece set in, and finally a door frame will be set into that piece of wall. And so it's the shape of the box that you make which shapes the final product. So in this case, a chalk building which is all circular, and therefore you have to be able to make circular formwork this. And now we sort of come to the heart of the material, really. First of all, you have the box, the formwork, and in this case, it's a concrete formwork hired from the concrete industry. On the inside face, it's more of a smooth curve, and on the outside face, a series of flat faces which will have insulation put against them to meet modern building regulations. And behind you can see a white earth material, that is chalk, and it's been moved from the hole that the building sits into, out of the hole, and then back into the hole again to form walls. And here you can see a little front end load, and Miguel is taking material out of the bucket and putting it against the face of the formwork, and then the rest is tipped in. On the left hand side you can see Ben with a pneumatic tool ramming. And on this case, in this job, we had 5 of us working, 2 carpenters, because the curved formwork is a little bit more complicated to assemble, and then 3 people running the digger and the rammer and filling. This is the first piece of wall that came out of that formwork. It's 6 meters long, 2.5 meters high. It took a day to produce, and it then connects together with other pieces which we're building, what we call hit and miss. So you can see there's a series of sections of wall with gaps in between, and so we're letting the earlier pieces of wall dry a little bit to shrink a little bit, and then we're filling in between and making a solid continuous wall. And in this way, we're reducing the shrinkage between one piece and the next. Other things to say about on this image that you can see, curves are being produced which are simple curves, and also complex curves in the middle there. So it's really a question of understanding the geometry of what you're trying to build and understanding the formwork that you're trying to build with. And here we're actually using commercial concrete formwork, and we're making it do something that it wasn't necessarily designed to do, but in fact it does very well. And you can also see heavy waterproof covers on the tops of the walls, and these are pulled down over the walls every night at the end of the day to keep them dry if it rains, and then in the morning they're lifted back on top to allow the wall to continue drying. Rammed earth is and that you can see that in this case it's holding not only its own weight, which is considerable, about 1.7 tons to the cubic meter in the case of chalk, but it's also holding big masonry domes, and they've got earth green roofs on top of that. Something slightly different. This is a classroom in the southeast of England, and this is a classroom built to passive house standard, passive house being an energy code, and it started out as being really about insulation material and controlling the temperature inside a building through insulation. But more recently, people have started to work with mass. So on the outside, you can see wood timber cladding, and on the inside, you can see rammed earth. And the line where the window meets the wall, you can see that there's a lot of insulation material on the outside and the mass of the wall internally. And this is something quite relatively new for passive house, that it's combining mass with insulation. So any heat that's captured in the building through sunlight coming through the windows. This is a classroom, so there'll be 30 people inside, and they're hot, and they might be using computers, and they're hot. Instead of the air temperature rising, the wall temperature rises. And when they go home at the end of the day and the sun goes down, the temperature that's locked in the wall then comes out. In fact, this is a funny building because it's one of a group of buildings that share the same heat source, and what they understood was that they should have put a control switch to that building to be able to turn off the heat coming into the building, because if you have a radiator in that building running for more than a day a week, the whole building overheats. And so they actually have to turn off the heating on Monday evening and leave it off for the rest of the week. This is local authority work. This is built by an education department of a local authority, and we have very little control over them as a client. But the people using these buildings were so happy that they went back and said, if you have more buildings to build in the area, you should do it like this, because more buildings like this would allow us to employ more teachers and pay less for heating. And so the local authority built a whole load more of these, and this is an example of the later build. So you've got the rammed earth walls with timber frame on the outside, which holds the timber paneling and also the insulation that will sit against it. But because the walls are inside, they're the load-bearing element. They're holding up the roof. They're holding the insulation on the wall, and there's no cold bridge. There's no problem with heat escaping through elements which are not insulated, because the insulation's on the outside. And so this is one of the finished examples, and it's a funny thing, but for me, because I'm a subcontractor and I'm a consultant, I want people to use the material, but I cannot control the way that it looks, and I can't control the way that it's finished. So in this case, you have electric conduits which are fixed to the face of the wall on the inside of the classroom, and I don't think it looks very nice, but that is under the control of the main contractor, and it's a level of control which I have to let go in order for people to use materials which are more environmentally friendly. And they're difficult decisions to make, because sometimes you'd like to make something that looks a bit more interesting, a little bit more attractive perhaps, but in order to get the normal construction industry to use these materials, you have to let go of some of this control. So again, this is the outside of the building. Looks like a timber building. Inside the building, it looks like an earth building. Most of the work that I've done in the UK has been in public buildings. There is a model which we saw in Australia, 1980s and 1990s, where people were building houses for clients. So these would typically be one-off houses, and one-off houses tend to be more expensive than mass housing, and so you get a certain kind of clientele, and that clientele tends to be conservative in their attitudes, and so they have been more insistent on the use of cement in the mix. And so when I came back to the UK from working in Africa, where the whole reason for working in Africa with Rammed Earth is that the cement is not affordable. When I came back to the UK, I didn't want to fall into that trap of building one-off buildings, having conservative clients who are then insisting on the use of cement. So most of the buildings that I've done have been public buildings, and in that way you get to work with designers, engineers, architects who are appointed by the client, and the client gives a lot of responsibility to those professionals to say, okay, you're the designers, you're the professionals, you make the decisions. We won't tell you where the window must be or where the door must be, which are conversations which tend to happen more in this one-off, more expensive housing situation. So it's a situation which I prefer, this public buildings, also because in this case it's a public building, it's a commercial office development. People go and work there every day. They don't have to buy it, they just have to experience it, and they find actually this is quite an enjoyable building to work in, and then later on maybe they'll think actually we could build a house like this. So it's a kind of a marketing strategy, if you like, to think about public buildings rather than private residential. Having said that, if somebody were to offer me the opportunity to build 50 houses or 100 housing units, that would be immediately very interesting. So we're back to the same commercial concrete formwork. It's been hired from a company, it's delivered on site, it's quite expensive, you have to immediately begin using it. You have to be very clear about how you're going to use this material, because as long as it stays on site, you have to pay for it. On the back wall, you can see they've made a full wall of panels, and this is a safety element so that someone can't fall out of the back. And then at the front, the formwork is built up in layers of 600 millimeters in height at a time. They're filled, each layer is filled with approximately 6 layers of loose material, and the next layer is put on. Most of our work is using material that we find on site. In this case, this office development, what the site had was sand, and so we had to bring in clay, and in this case it was 10% clay and 30% stones, gravel, and that was added to the sand that was found on the site. This mixer was used to mix the material and put into bags for storage until it was required. And then we're using a commercial scissor lift with a box built on top to deliver the material up to the 6 meter or so height. So there you can see the loose, moist material being shoveled into the form, and then it's compacted, I say in 100 millimeter layers, and the next layer of formwork is put on. This office building is a funny story because, again, it was built by a developer who was working for a local authority. They took 80% of the building for their own use, and after 7 years, after the financial crash of 2008, they couldn't afford, the local authority couldn't afford to stay there, and the developer was faced with a building that was going to be empty and would be a cost to them. But within 6 months, they had completely refilled it. And this is in an area where there's a lot of concrete, steel, glass office building, which is empty because of the economic problems. And this particular building didn't have those problems because it is so different. It's comfortable, it's attractive, and the developer realized that what they needed to be doing was more buildings like this and less buildings in steel and concrete, which are of which there are a lot and which people don't particularly like. So that's the sort of the building side of things. Some of the work that I've been doing, some projects that I've been doing, a little bit of the thinking about how to introduce a material like rammed earth into a modern construction scenario. There's also another whole context, which is about rules and regulations. I talked about this at the beginning in terms of monopolies and cement. And we've been dealing with this since we first started building in Africa. So in the early 90s, we applied for a grant to write a description of what we were doing. And the upshot of this grant was this book. Julian's my father. He was an architect. And we worked together over a number of years, and we produced this code of practice, which is highly illustrated and is very much about owner builders, smaller builders, builders that don't necessarily read. So the code is split into illustrated and written, and it became the basis of the Zimbabwe Standard Code of Practice for rammed earth structures. And this standard happened because we sat in committee meetings for a couple of years. Every month you'd go. It's a voluntary system, so you just go. You don't get paid, and you go through the document line by line, and eventually it's published as a national standard. This was published in 2001, and that allows people to build with a degree of security, that they understand that these are limits that have been tested and that they can work to. It also means that you can build within an urban center. In Africa, you can build with what you like once you've got out of the urban center, but not while you're in a city or a town. And this also means schools, because schools are typically funded by the government, and so they follow their own city rules, even if they might be building in very remote rural areas. And you'll see a little bit more of this later on. But this is why we did the standard, was to allow things like schools and clinics to be built in urban areas or outside of urban areas. And from there, we were invited to talk to the Southern African Development Community, which is a group of 15 countries you can see there on the map. And this is somewhat the European Union. It's a group of countries that have agreed to cooperate to increase trade. And to increase trade, you have to remove barriers to trade, and that means standards. And so we were asked to try to harmonize the Zimbabwe code on earth buildings across the group of 15. And that took quite a long time. But it was a very interesting piece of work, because then I realized how much further behind Europe was falling in terms of regulation on this kind of thing than Africa is. The Rammed Earth Code of Practice was harmonized in the 15 countries in 2012, and we're now working on all Africa. So about the same sort of time that was going on, we were asked to peer review an American standard, an ASTM, the Standard Guide for Design of Earth and Wall Building Systems. It's a very interesting, very general document. And for places like Serbia, where you're not allowed to build new buildings, I think it could be quite an interesting way to start, because it just generally says if you have existing earth building, you can build to that same standard in a safe manner, and that's a big leap forward. Obviously, one standard cannot cover the whole earth building technology family, and it can't cover all of the different countries and all of the different regions and all of the different situations. but it is a start. And so we've begun in the UK talking to the British Standards Institute about introducing this as a British standard, harmonizing it. So we don't rewrite the standard, we just harmonize what is already there. And I'm sure that you'll find that the Polish Standards Organization has an agreement with ASTM in the States, and it's a discussion that you could have with your local standards body. And it's that kind of action, that kind of activity, which opens up the possibilities for other people to use these sorts of documents. I mentioned Serbia because we're working with a group of European countries, of which Serbia is one, to write training standards. I'll talk a little bit more about that. And Serbia is one of those countries. And so I have a little bit more knowledge about the regulatory situation in Serbia than I do in Poland, but it may be the same or it may be different. I'm sorry, I don't know. About the same time as well that we know, a little bit earlier than starting to do the work with SADC, we started working on a UK guideline. Eventually, it would be nice if this became a standard. Again, we're a little way away from that at the moment. But this guideline, it's more UK based than the code of practice I showed you. It talks about insulation. It talks about issues that that prevail in Northern Europe, as opposed to the code of practice, which is looking much more at Africa. And over its lifetime, I think it was published in 2004. It has grown its own. Influence. So it's the basis of the BREEAM guide for rammed earth structures, energy rating for rammed earth structures, and rammed chalk structures, all of which have an A+ rating. Now, people say that BREEAM is or is not accurate or rigorous. The main thing for me is that rammed earth should be on a list of building materials, and cob should be on a list of building materials, and adobe and other earth technology should be on those lists, and that's why we've worked to put it there. And at the same time, it's gone into something called the National Building Specification, and this is an online tool for architects registered with the Royal Institute of British Architects, and there are stations on everything from roofing materials to foundation materials, everything to do with buildings. And they also have a specification for rammed earth. Again, it's not a national standard, but it begins to change the framework within which people work. And recently we were on a site and the architect instructed the contractor, according to the National Building Specification, you have to put some money to one side for testing of materials. And that's normally my line. That's normally what I have to instruct the architect, and that's normally what I have to instruct the contractor. But once it's in the National Building Specification, the architect begins to instruct the contractor on these things. And that makes the whole thing much easier to work with. We also set up Earth Building UK. There are a lot of bodies in the UK to do with sustainable construction of one sort or another. But finally, we decided that we needed our own earth building group because it's sufficiently different to people who are trying to sell ground source heat pump or other organizations that we're happy to cooperate with. And in fact, we would very much like there to be a straw bale organization in the UK, but at the moment there isn't one. Once there is one, you find that it's much easier to talk to organizations, to state structures, and bring your point across. And to work with, as I say, this group of European organizations, we're now working with 8 countries in Europe to write training standards. Again, I can talk to you about rammed earth structures, but how do you actually learn how to do this? well, maybe you come over and do a workshop with me, or maybe you go and work on a building site somewhere in France. When you go back to Poland, you don't have a qualification. And so this is what we're trying to change, is to work within the European context where you can take a bit of training in one country, get a certificate, and take it back to your own country, and that certificate then is recognized as part of your lifelong learning. And so that's something that we're really quite interested in. We're just coming to the end of a 3-year project. Soon those materials will be available online for free to download, and they join a suite of materials already available and being used in Poland on clay plasters. This is the next part of that. This is the clay plasters, which are all downloadable now, and they're a very detailed set of documents, and they're free, and so please help yourself. Earth building generally is getting a slightly higher profile than it did in the past. UNESCO has recognized earth as a building material, as a second building material, as a building material which houses about a third of the population of the world, a little more than 2 billion people. And here you can see their website advertising Earth Building UK's festival, which we've just completed this June, where a lot of people came and ran workshops from across Europe and the States, and spoke at the conference. People came from Africa, and quite a vibrant festival, actually. Behind all of this, there is research work going on. These are samples in a lab that we prepared in the making of the guideline, and you can see samples which have been broken or eroded or crushed or in various different ways to tell us more about the strength of these materials and how the strength of samples relates to the strengths of whole walls. Sometimes it's done in the lab, sometimes we do this sort of work on site. This is a wall that we built in an area where they experience high wind loads, 105, 110 mile an hour. And so we built a wall, and then we put a lateral, a sideways load on that wall, equivalent of about 350 mile an hour wind. And the wall moved by 3 millimeters. So we were very happy about that. The engineer was very happy about that. And quite often you have to do these sorts of things on site, in situ, because the material that you're using is not a British standard material. In this case, it was dug up on site. It wasn't a particularly strong material. It didn't have very strong strength characteristics. It was quite easy to abrasion to work on it. But it did have very good lateral strength, and that was the thing that was most concerning to the engineer. This is a more sort of typical full-scale test going on in a lab, where the newly formed column on the left is 2.8 meters, took 45 minutes to produce, and you can see it's a darker color because it's still wet. And then on the right-hand side, it's a paler color because it's dried. And it's failing at a little over 10 tons of load. And so I normally say to people, that's a London bus that's been put onto a 350 millimeter square column of clay and sand and gravel, which has been put into a formwork and compacted to its optimum density. Rammed Earth is about formwork. It's about the shapes that you can make, and in this case, the shapes that we're making are fabric. And nobody's used project yet, but they're quite fun things to play around with. It's one of the reasons why I continue to be interested in Rammed Earth, is that people are continually proposing different things to do with it, and each time we do something with it, we find that it can do things. This is a column. And this is back to a straight wall, which looks like this when you take the fabric off. So we haven't really thought of an application except that we've built 2.5 tons of wall with about 10 kilos of fabric. There's something quite interesting about that, but more work is needed. Yeah. So then this is a lecture theatre we built in Wales, and it comes back to various points that I've been speaking about in terms of the office development and so on, where the architect, the engineer, the contractor, none of them are specialists. So my job is to help them understand what is necessary to build these structures. I'm not an engineer, I'm not an architect, I'm not a surveyor, I'm not a contractor, I'm a consultant now. And so it's really about helping them understand what these materials can do. So this is a lecture theatre at the Centre for Alternative Technology in Wales, and the walls are a little over 7 meters high. They come, in this case, from a quarry. This material is limestone, and the dark lines in it are clay. So it's a valueless material until the clay is washed away, because the concrete industry and the roads industry, tarmac, will not accept limestone with even 1% of clay. And so that's an opportunity for us, because all of this material has clay in it, and we have to test the proportions, but all we basically pay for is the transport of that material to site. I would normally prefer to work with material that is on site, but in this case, the architect, the architect insisted on this particular material, this particular color from this particular quarry, and it was something that, again, we didn't have control over. But we could say what the formwork was like, and we could instruct the carpenters you can see here in the image, who are basically, they're site carpenters. They put formwork together normally for concrete works, and we're showing them just those little differences between putting formwork together for concrete and putting formwork together for rammed earth. And so I think I worked with them for a day and a half, and they completed the project, which has all the normal health and safety issues, access issues that you would expect here. And it's producing a public building, a load-bearing public building. It's holding the roof, and it's a very high specification energy building, meaning that it doesn't get a lot of heating, but collects as much solar energy as it can, and the energy from people inside the building. A much smaller project, but working with children, with boys mainly, who are failing in school, and with this big double reciprocating timber roof. It was built in a wood. This is the opening of the building. It was built in a wood, and just at the front of the shot here, we're looking over a pond, and the pond is where the soil came from, and the trees are where the roof came from. So this building is really very short distance indeed. Normally, in a building site situation, the use of the pneumatic tool is shared among workers. In this case, the workers are boys between 16 and 19, and they really wanted to use that tool, and they'd almost fight each other to get their hands on it. It's kind of unusual situation. There you can see beyond the building site the pond where the material for the walls comes from, and beyond the pond you can see piles of soil, some uncovered and some covered. We have to keep the material as dry as we can, because it goes in this just moist state. It's not mud. It's not a wet material. This is the team. going from right to left, the guy on the right-hand side his job is to look after these young men, these boys. He started his job at this place on the Monday morning, and before that he'd done 20 years working in restaurants. So not a lot of building experience there. And then you've got 3 boys and a girl, and they've left school without qualifications. And then you've got the architect, and then you've got me, and then on the far left you've got Bob, and Bob can drive a digger and has got building experience. So I worked with them for a week and went away, and they built the rest of the building. So it's a technology which you can put in place quite easily with quite low resources in terms of skills and knowledge. So here are our freestanding sections, and they will have, I'm sorry, I'm going to go back. They will have lintels placed across the openings and walls built over the top, and the roof is then placed on top of that. When they came to placing the roof, I said that I'd like to be there to fit the timber plate that the roof sits on. It's fixed down on bolts which you can see poking up from the top of the wall. And so I was there for a day fixing that plate. And then the client took me back to the station. And as we went, he said that he was concerned that these walls wouldn't be able to take the load of the roof. And this is a very common perception, that earth walls can't take load. This is a circular building inside, and on the outside it has 12 flat faces. Each of those 12 faces is 6 tons. We did a little calculation to show that the whole roof was 6 tons. So effectively, it's like building another 12th in height onto each of these wall sections. Not a lot of load really at all. But people have this perception that roofs are going to be heavier than they actually are. That's one end of things. Then another end of things is a site in the southeast of England where the client wanted to build the building themselves and with volunteer labour. And volunteer labour is something that's been used quite a lot in things like straw bale. People have built a business model on that way of building, but it's more difficult with rammed earth for various reasons. It's really hard work apart from anything else. And so I said, how many volunteers do you have? And they said, we don't really know, because that's the nature of volunteers. We don't really know, but we think between 2 and 30. And so in this case, we had to buy a lot of second-hand scaffold planks again, and these cost about £300. And so we could make a formwork up that was 20 meters long, so that if 30 people arrived, they would be fully employed. And if 2 people arrived, they hadn't spent all of their money on hiring in expensive formwork. So these are the kinds of things that you have to think about. This is the same building, and you can see that it's got rammed earth. They had a roof in place that we're building under, and so the gap between the top of the wall and the roof was filled with adobe bricks, which they had made, and the outside is insulated with straw bale. Very nice combination of materials. And that's the building facing south. A lot of thermal mass internally, a lot of insulation externally, with big south-facing triple glazed windows to capture as much heat as possible. Now, I realize that I've now got about 10 minutes left, so I'm going to go a little bit faster. Earth is about what you can cast. It's about the shapes that you can make. And this is a building that was built inside of a barn. And the formwork, again, is very simple. Formwork made from sheets of plywood and a frame. The client here had used these 10 years previously on another building project and kept hold of them and then used them again. But this time we were making thicker walls because this is a plinth that a building stands on. And we're putting in a very simple block out to make arches. And these simple shapes can make repeated arches, and the more arches you make, the less earth you have to ram. So you can see that plinth is about the level of the ground outside, and the thinner walls are then built on top of that. You can see there, and you can see that there's a little ledge around the edge which the timber floor will sit on about 1.2 meters above the level of the barn floor. Just quickly then, a section on Africa, and you can see then we're working at one level with contractors, with a lot of equipment, with diggers, with all of the materials at their fingertips. We're working with people who want to work with volunteers, people who own a building. And now this is the other extreme, where all of the tools are without electricity and all of the material is dug by hand, and the formwork is made up from planks that we've bought, planks of wood that we've bought locally. And so this is just a very quick section to show you how a series of boards can be put together. Sorry, it loads a little bit slowly. I thought this would go a little bit quicker. These are being assembled, end stops. Now all of the material is being placed and rammed by hand. Once we're up to the first level, more boards are placed in. The next level is rammed. And you can see here that the bolts that go through, there's a series of bolts at the bottom of the wall, and there's a series of bolts at the top, so that there are actually only holes through the wall at that bottom level, and those are quickly filled with the same material that we're ramming the walls with. And the next level, then of course you have to think about access for the material. And the next level, next lot of access, and there is the wall. That was the first wall that they built. It was a group of 16 young people that we trained. This was their first wall, and this took a day and a half to build. So it can be quite quick, even working by hand, if you are organized and you manage your workforce cleverly. So you've got that first piece of wall there on the right-hand side, and on the left-hand side, we have the bottom of the same set of formwork set up ready. So as soon as they've finished their first assembly, they can move to their second. There's no waiting, and so you're managing the workforce effectively. And you've then taken down the first lot of formwork that you saw in the first lot of images, and that's making a third assembly, which you can see on the extreme right-hand side. It's the same corner setup as the first corner. So you've got one full setup and one starter setup, which means that you can keep the team working rapidly. And then we used a very simple old-fashioned steel set of formwork. You can see at the back of that shot to make curved walls. This is mixing lime with the material, thinking about making foundations. And this was the completed school building, all made by hand. So yeah, coming to the end now, and this is a project that we just did a couple of years ago in Holland Park, so it's very central London. This is unusual in that all of the material was brought to site. The client is a public park, and they said, well, you can't dig material on site. And when we arrived on site, we found that they were actually removing about 100 tons of soil from the site, but we couldn't use it. It was too late. And these are some of the frustrations of the work, is that opportunities are there if people can understand what the opportunities are, but they don't always, and it's difficult to explain to them. So inside the building, it's a kitchen and a series of toilets and bathrooms. This is our initial setup. this was done in the snow in March, and this is the building as it's being built with waterproof covers over the walls as we extend of them. And that is it. So I hope that's kind of been an interesting. For me, it's quite strange speaking to people that I can't see, but I hope that you have a sense of it. And if there are questions, I'm happy to answer them.
Thank you, Rowland. Do you hear me right now?
Thank you. Yes.
Thanks for the great introduction. I have 3 questions before I open the questions from the audience. But before that, I will a bit change the organization of the webinar here. Yeah. Okay, I will now switch off the moderation. So you guys please write questions in English. I will try to choose some of them. First question, could you speak or tell us more about the insulation inside or outside the wall? What kind of decisions do you make when it is inside or when it is outside or inside?
Okay. Most of the time, I mean, the thing is, like I said, I'm not the designer, I'm not the architect, and I don't get to make these decisions. When I am being a consultant, the designers will listen to me somewhat, and I can suggest things, but I don't have the final decision. But that said, normally we will advise people to put the insulation on the outside. Having the mass internally and the insulation externally means that you don't get cold bridges, you have that mass of wall inside which can absorb any free heat in the day, and you get much more even heating day to night. And this is true in summer and in winter. And so we would normally say put it on the outside, and then of course you don't see the earth on the outside. You have then to cover the insulation in some way with timber and so on. But for a lot of people, especially in public buildings, they are happy about that because they feel that there's a risk in having earth outside, and you take that risk away. So there's benefits to putting the insulation on the outside. In that case, we have done buildings which have had sheep's wool, blown cellulose, polystyrene, basically every type of insulation that's available has been put onto the outside of an earth wall. And it's one of the things that is also true about clients that are happy to work with or have an earth wall, is that they are much more willing to try a lot of different things out. A client that's happy with a PV cell on the roof won't necessarily have an earth wall, but a client with an earth wall will be very happy with a PV on the roof. Do you see what I'm saying?
Yes. Thanks for that. Another question is regarding colors. How do you manage to change colors of the wall? I know that you can use a different kind of clay, but maybe you also have other options to change color.
Yeah, I mean, traditionally in Spain they use lime, so they make a mix of earth and lime, and they just put on the outside layer, so they fill against the formwork just with the earth and lime, and then inside it's just earth. So 90% of the wall is earth, and then just that outside face is earth and lime, and it gives it a paler appearance. And that goes for all color work. It's only the surface that you see. You don't have to have a full layer of red that goes from one side of the wall to the other. It's only what you see on the surface. What I would caution about is that there's a lot of color work on Google, and you look at this picture on your little screen and you go, wow, that looks great. But when you actually visit the building, it's too much. It's just, you have to handle color very carefully. So I've done a bit of color, and yes, different colored clays and different colored oxides and lime. But go careful, that's what I'd say.
Okay. Next question is about waterproof, making the wall a kind of waterproof. What kind of additives you can add to make it more waterproof? Is it possible to add cement or lime to make it possible?
So, like I said, lime, yes, but I would just never use cement. I just don't use cement, and I would never use cement. If you want to use cement, then don't use earth, because earth and cement are really bad. They're a really bad fit. They just don't work together. It starts off good and it ends up bad. Other ways of thinking about this, we use a certain amount of, I'll just call it varnish. There's lots of different types, but it's a clear finish. So it's like a paint or some sort of painted liquid finish, but we would never use it on an exterior. I would much rather the wall washed away a little bit on the outside than try and put a varnish on, because as the varnish breaks down, you can't see it. If you painted it white and the white paint began to degrade, you could see, oh, now I need to repaint with white. But with a varnish, you can't see that, and so it's better just not to do anything, because if you put that waterproof coating on, it will fail at some point, and it will lead to more problems than putting nothing at all.
Okay, thanks. One question from the audience was about the basement. Is it possible to make a basement in this technique?
I'm going to assume that this is a Polish question and that you have strong minus temperatures, below zero temperatures, and therefore I would say if you do a basement, probably better to do it in brick or stone. You can do a basement. You can use lime to keep the strength of the rammed earth higher when it's wet, but this freeze thaw is something which we don't know enough about. There's more research to be done.
Yes. Okay. Could you tell us more about the possibility of putting some installations inside this kind of walls?
Fixings.
Yeah, fixings.
Yeah. Okay. So you can either fix
fixings, yes, but also kind of pipes, water pipes, electricity, and stuff.
Okay. All right. All services as well. So fixings. In Africa, all fixings are built in as we go. And in the UK, it's a bit of a mixed story. Sometimes we're building fixings as we go. So that might be timber elements which are tied into the wall, which mean that you've got something to fix to easily, shelves or whatever. Or it may be roof elements. But people here also drill after they've fixed and use epoxy resins and other kinds of fixings into the wall. And it's the way that the industry is structured here that I'm the wall person. I do walls, and the next person is the roof person. He does roofs, and the next person, he's the plumber. He does plumbing, right? And we're not the same people, and so they like to keep things all nice and separate. Doesn't really matter. All of them work. Wires is fine to go into the wall. We would normally try and build a plastic conduit into the wall to pull the wire through. Water and gas, okay, they're dangerous things. And in England, people go to a shop at the weekend and they buy a big drill and they go home and they drill holes into their walls and they put up shelves, and they're not professionals, and if they drill into a water pipe, then it will be a problem. So I'm a bit cautious. You can put water pipes into the wall, and people have done this for heating and so on. It's a very nice idea, but I'm a bit cautious about it because you don't know who the end user will be.
Okay. Okay, next question. How from Marumatko, from Marcin Mateusz Kowski, you probably met on ebook a few days ago. He asked about how do you manage to convince the building inspectors that Rammed Earth could be the load-bearing structure or wall?
So in the UK, we have an expert-driven industry, and that means that as long as you have an engineer who will generate a design and will submit that to the local building regulator, then they're happy. They don't mind. But it does lead to walls being, sometimes they're over-engineered because the engineer is looking to his own insurance, which is what guarantees his or her work. And but once you pass that hurdle, then the local authority, they don't mind.
Right.
But this is what we're working towards, standards and norms, which I talked about a bit, to get to that situation where you can just give the calculation to the local regulator, and they have the standard they can follow, and they can say, yes, it's 300 millimeters thick, it's single story, it's taking this roof load, fine. That's the situation I would like to get to, but it takes a bit of time.
Okay. Could you tell us a bit more about the place over the window, the lintels? How do you construct them?
Just like you construct any lintel, could be timber, could be concrete, could be steel, could be, but I guess I'm happiest using timber. It just seems like a more natural fit, but we've used everything. We've used old telegraph poles. We've used a lot of different things. And there's different ways of forming openings and different ways of fitting windows. You might build a window in as a complete piece, or it might be like the example that I showed where the walls are left with a little return on them, and the lintel is placed on, and then more formwork is put on to connect the two sides of the window. There's different ways of doing it. Doesn't really matter. The main thing is that the lintel must be able to support the load.
Okay, are there any limitations for the window sizes? Paulina is asking.
The limitation, I suppose, is the opening size. It's how deep the lintel goes. How to explain this? The lintel has to sit on a wall at either side, and the wider that opening is, the more lintel you need to sit on the wall on either side. Also, the wall above is heavy. So I said that chalk walls are 1.7 ton to the cubic meter. A normal clay material is more like 2 tons, 2.2 tons to the cubic meter. So you have it's a heavy lintel to hold that load, and then you've got how much of that load is carried into the wall on either side. So it's just, these things have to be calculated.
Yep. About calculations, Marcin is asking about how do you calculate working hours per square meter ratio? How do you calculate how many working days needed per 1 square meter of the wall? More or less.
Yeah, okay. So I would say that a working team should normally be, if you're working with machines, so you've got a digger, and you've got a compressor, and you've got a pneumatic tool, then a working team is 3 to 5 people, and they should produce about 6 square meters a day. If you're doing simple work, straight lines, then normally you'd be doing more than that, but we calculated on that for 2 reasons. Number one, it can rain, there can be delays, the machine can break, and number 2, if you do achieve better than 6 meters, then that's more profit for you. which is an important thing. It's one of the important things about working with non-specialists, particularly contractors, is you have to show them how to make money, because that's really what they want to do. And then if it's a manual team, we would normally think of a manual team as being 9 to 12 people, and we again think about 6 square meters a day. And so then if you've got a program which says, you know, that you have to complete the work within a month or 6 weeks or whatever, then you have to have, then you'll have to have 2 teams working, both doing 6 square meters a day, or 4 teams, or 8 teams. It's just a question of fitting the work rate to the program that you are obliged to.
Okay, thanks. It would be the last questions in this session. Could you tell us about the minimal width of the wall in relationship to the height?
Our minimum is 300 millimeters. You can do smaller, but one way and another, it becomes more awkward to work with. So 300 millimeters is our minimum, and so you can go from 300 millimeters. We've done 2-story work at 300 millimeters, but normally the wall begins to get thicker as the wall gets higher. So it might be 350 millimeters or 400 millimeters on the ground floor, and 300 millimeters on the first floor, or it might be 450 millimeters on the ground floor, 400 millimeters on the first floor, 300 millimeters on the third floor, or it might be 500 on the ground floor, 450 on the second floor, on the first floor, 400 on the third floor, 300 on the fourth floor. Do you see what I'm saying? So it's getting thinner each time. The lecture theatre which I showed is a little over 7 meters high, so it's sort of 3 stories, and that was 500 all the way up because there was no change in side, and so they wanted it to go up evenly, and so it's carrying a lot more load than it really needs to, its own weight. But in a normal situation where you're going up and then there's another floor and another floor, the walls would be getting thinner.
Okay, Rowland, thank you very much for this all those presentations and answering all questions. This is like a great introduction for this technique. I hope everybody who joined this webinar today are motivated to study more. This is the purpose of this webinar, to inspire more people to study this technique. I hope we will meet virtually because next week, because guys who went to your conference, the Earth Building UK, a few days ago, are preparing presentation from this conference. So yeah, we are going to spread more information about the Earth Building in Poland. So thank you for your work, and thank you that you was here with us and sharing your experience.
Thank you very much for having me. It's been quite strange, I must say. Normally I can look at my audience and see how they're reacting. So hopefully they could understand what I was talking about and didn't get too lost.
Okay, thank you. Most of the people were able to understand you. Few or not, but we will try to translate with the help of the community. So probably in the near future, everybody will be able to understand. Thank you one more time.
Okay, good night.
Goodbye. Ja już przechodzę na język polski. Jeszcze chwileczkę chciałbym Was zatrzymać i halo, halo? No już chyba jestem, coś tutaj, coś nie zadziałało. Słychać mnie teraz? Okej, jest. Bardzo Wam dziękuję za dzisiejszy webinar, dziękuję Wam za uwagę. Na początku nie było mnie słychać, mimo że 5 minut się produkowałem, robiąc wstęp, natomiast nie było mnie słychać. Przypomnę, że Te webinary robimy raz lub 2 razy w tygodniu, organizując taki wstęp do tematów związanych z kulturą trwałą, czyli taką, która jest w stanie trwać przez tysiące lat, nie unicestwiając siebie samej. Dlatego podejmujemy różne tematy, między innymi architektura, tak jak dzisiaj, ale też związane z energetyką, edukacją alternatywną. Było o zdrowej żywności, o cohousingu, także zapraszam Was na następne webinary. Już w sobotę na przykład będzie o projektowaniu ekosystemowym w duchu permakultury. Wejdźcie na Facebooka, tam na pewno znajdziecie więcej informacji na ten temat na naszym kanale. Słuchajcie, dziękuję wszystkim bardzo gorąco tym, którzy wybrali zaproszenie dla fanów, bo to właśnie dzięki tym osobom ten cały powiedzmy wirtualny serial webinarowy w Cohabitacie może się dziać. To właśnie dzięki tym osobom możemy opłacać koszty działań, koszty realizacji tego przedsięwzięcia. Ogromne dzięki i podziękowaniu dla Was wysyłamy zapis tego webinaru po 36 godzinach. Dla wszystkich innych te webinary są dostępne po kilku tygodniach na naszym kanale na YouTubie. Przypomnę, Cohabitat TV. To tyle, słuchajcie, z naszej strony dziękuję Wam wszystkim za uwagę. Dziękuję Agacie, która przygotowała tą część prezentacyjną i obsługiwała i odpowiadała na Wasze pytania mailowe i również na Facebooku. Dziękuję wszystkim za wyrozumiałość, gdyż tutaj było parę potknięć technicznych, ale mam nadzieję, że wynieśliście swoją inspirację. Tu odpowiadając na pytanie kogoś, kto się pytał, jaki jest cel dzisiejszego spotkania. Celem dzisiejszego spotkania było to, żeby zrobić pierwszy krok w kierunku zapoznania Was z techniką Rammed Earth, czyli gliny ubijanej. Absolutnie nie było celem podawać Wam tutaj szczegółowe przepisy na to, jak to zrobić, gdyż to nie jest tutorial, nie mieliśmy na to czasu dzisiaj. Natomiast przygotowujemy się do takich zadań w przyszłości. Chcemy zrobić kursy wideo dotyczące tego tematu. Także śledźcie nas, chcemy to rozwijać, a zapraszamy Was do tego, żeby czytać książki. Było dzisiaj na prezentacji podane 2. Jedna z nich na pewno jest dostępna w sieci, w PDF-ie można ją znaleźć, także możecie głębiej poszukać na Google'ach. I to wszystko. Dziękuję Wam za wspólne uczestnictwo w tym skromnym show. Do zobaczenia w sobotę i na kolejnych webinarach. Cześć!